Let's look at a more detailed relationship between continuous variables. Identifying the relationship between two sets of variables is extremely common. And when they're related, they will tend to move in the same directions. We saw this when we looked at the Old Faithful data set, where we had the x-axis as the eruption time and the y-axis as the waiting time. And we could see that there was an upward relationship. Some other examples include, as disposable income increases nationally, retail sales increase. As obesity rates increase globally, life expectancy drops. That might be a negative relationship. As temperature increases globally, sea levels increase. Again, that would be a positive relationship. These numerical relationships can easily be seen by the scatter plots. So let's go back to that relationship that we spoke about Old Faithful. To the right, we've got the same data set now here, and the full data set contains 272 points. An analyst looking at the numbers might think that there is a relationship between the two numbers, because it seems that when the waiting time is longer, the eruptions might be longer. Since both numbers are numeric, let's use a scatter plot. When we do the scatter plot, and recall this is an XY coordinate scale, Cartesian coordinates, the scatter plot will show that trend clearly. We can see that there is a relationship. We can see that there's that red line, and an analyst can use this to determine that there's a connection between the two, but we're not sure what that relationship is. So what we want to do is we'd like to quantify numerically what that relationship is. And we do that by using what's called a covariance and a correlation. Now, ultimately, they will tell you the same thing. Covariance measures how much movement there is in one variable, which will predict the movement in another corresponding variable. And correlation will standardize the covariance, making it scale invariant. In other words, I can compare it with two different scales. So again, this is going to look like a crazy formula, but we don't need to do much here because Excel will do this for us. But to understand what's going on, we're looking for how much change and the direction of the change between these two variables. The way we do that is we're going to measure how much movement in one variable predicts movement in corresponding variable. To calculate a covariance, we need to measure how each observation in one differs from its mean, x bar, and see how the corresponding observation of the other variable differs from its mean, y bar. So here you'll see the two parts of the formula. Each observation minus its mean times its corresponding y value minus its mean. And we add those all up, and then we divide by n minus 1. This will give us the covariance. In Excel, we could just use the covariance of the first column and the second column to obtain the covariance. The problem is that the covariance will give us a number, but we really can't interpret it well. The correlation will standardize the covariance and make it scale invariant, allowing us to compare two variables with different scales. If we have two variables such as grade scores and height of students, we have two variables that are on completely different scales. Using the covariance with the two variables is going to be very difficult to interpret. However, the correlation, which we generally represent by the Greek letter rho, is more widely used in interpretation. The rho is going to look like a lowercase p. Because it's scale invariant, it means that the scales don't matter. This is what happens when we standardize any metric. Thus, the formula for the correlation is going to be the covariance of x and y divided by the standard deviation of x and the standard deviation of y. We can use the formula correl to obtain the correlation between the two. We'll also show how to use the data analysis tool in the Excel modules that we have so that you can easily compute the correlations. Here, if I have the two, I'm going to ultimately compute the correlations, but it gives us an easier way to interpret it. Correlations that are less than 0 are going to be negative correlations, and it means that the two are negatively correlated and that they move in opposite directions. As x goes up, y goes down, or vice versa. All of the numbers will always be between -1 and 1. So they'll range from -1 all the way to 0, and then from 0 to +1. The positive correlations will be greater than 0, and it means that the two variables are positively correlated. They move in the same direction. As x goes up, y goes up. Correlations that are close to 0 means that there are no correlations and therefore independent. In the case of this data set that we have, we computed a covariance of 13.93. And we could see that 13.93, because one is, the eruption time, the waiting time. What does the 13.93 mean with regards to this? Does it mean it's in minutes? Does it mean it's in seconds? How much does that mean? But if I take the correlation, I now have a result as 0.90. That means it's positively correlated, and it's a strong correlation. So therefore, it's easier for us to use the correlation for interpretation. In advanced statistical methods, we will use the covariance for a number of different reasons, but not for this course. Here's what some of these look like graphically. If you have a correlation of 1, it will be a perfect straight line. And if it's correlation of negative 1, it'll be also a perfect straight line. One will be going up, the other will be going down. These are called perfect linear correlations. If I go below these, I have a correlation of 0.89. You can see the dots going kind of like straight up, and it forms a good general line, but they're not all in line with each other. And correlation of negative 0.74, a little bit more scattered than the 0.89. But these are linear correlations, and we can see the increasing and decreasing trends. Moving to the top right, I have a correlation of 0.04. This creates a cloud pattern, and we can see that this really shows no obvious pattern, so there's no correlation. Now we look at the bottom one, and the bottom one says looks like a pattern. There looks like there's some relationship. But, and even though the correlation is 0, there isn't really a linear correlation. This is what's called a curved linear correlation. So the correlation values are only used when we're trying to identify a linear correlation or a linear movement between variable X and variable Y. There are other ways to do this, but that's not for this class. So while there are some statistical tests that can be used to determine the strength of correlation relationships, there are a few guidelines that we could use. The more data points you have, the more accurate the guidelines will be. If there are 8 data points and the correlation is 0.4, more data can have a significant impact to the result. There's also no magic on the data points. Some books refer to 30, some refer to 50. The idea is for the analyst to take a good close look at the data and see if we have enough to make a conclusion. And you determine if the data is sufficient to make a conclusion. However, there are some additional tests such as effect size, power, and normality of data. But in general, the guidelines that we can use are this. If you have something from -1 to -0.8, it's a very strong negative correlation. And then roughly every, 0.20 between that. -0.8 to -0.6 is strong. -0.4 to -0.6 is moderate. -0.2 to -0.4 is weak. Anything from -2 to 0 or 0 to 0.2 is 0 or no correlation. And then we move the reverse way. 0.2 to 0.4 weak, 0.4 to 0.6 moderate, 0.6 to 0.8 strong, and then 0.8 to 1 very strong. We do have an easy way to compute this. Microsoft Excel provides a statistical analysis tool called Data Analysis Add-in. In order to do that, you're going to have to install the Analysis Tool Pack. And when you do, in the ribbon bar under Data, you'll see a Data Analysis Add-in. What we'll do is we'll choose correlation from the list of options. Then what we'll do is we'll select the input range of the columns to perform the correlation. So I can have any number of columns. I could do 7 or 8 of them. We just need to make sure that they're all numeric. The input columns together, they have to be together and continuous. You cannot skip them. I'd recommend you choose the labels in the first row so that when it creates the table that you'll see below, it'll actually give you the headers instead of variable X1, X2, and so forth. And then what we'll do is we'll put the output range on the same sheet, or if we could put it in another sheet if we wanted to, and it gives us a nice correlation table. The correlation table is a matrix here that is only the lower triangle, what we call, part. So each one on the diagonal will always be 1 because that's the variable correlated to itself. So it will always be a perfect correlation. They will always move in the same direction because it's the same value. So we're not really concerned about that. But then when we get below, we're looking at the day and duration and day and interval, and then the other one is duration and interval. And that's the one that we're looking at here, which is 0.87. So that means there's a 0.87 correlation between the duration and interval, which is a very strong correlation.